So before starting with eigenvalues and eigenvectors, we should know what matrices are. Okay, so we'll just go through matrices. So matrix is basically an array of elements. In this case, numbers. Okay, so an array means a setup which has a particular rows and columns. So for example, if I define a 2 cross 3 matrix, so that means it has 2 rows and 3 columns. So I'll fill in the entities here. So 2 rows and 3 columns. So 1, 2, 3, 1, 1, 1. So this is an example of a 2 cross 3 matrix. Okay, similarly, you can have a 2 cross 2 matrix, which is 1, 1, 0, 1. Okay, and matrices where the rows is equal to the columns are called square matrices. So the matrix on the right, which is 1, 1, 0, 1, is a square matrix. Now, matrix, like the square matrix on the right, have a lot of applications. And the 3 main applications in the AIHL syllabus are systems of linear equations. The second one is Markov chains. And the third one, and the example which we'll be seeing now, is 2D or 3D transformations. In fact, to be very specific, 3D transformations are not a part of AIHL syllabus, so we'll just exclude them as of now. Okay, so the only type of transformations which we'll see using matrices are 2D transformations. Okay, so let's see how transformations in 2 dimensions is achieved using matrices. Okay, and to be very specific, 2D transformations on vectors. What we are transforming here are basically vectors in 2D plane. Okay, so firstly what I'll do is I'll consider the 2-dimensional plane with the y-axis and the x-axis, and I'll consider a vector from the origin to the point 1, 2. Okay, so this is basically the position vector to the point 1, 2, because a vector whose tail is at the origin is called a position vector. So this vector can be represented as 1, 2. Okay, now suppose I want to stretch this vector horizontally by a scale factor of 3. So to achieve a horizontal stretch by scale factor 3, or the same transformation, you can state it as stretching by scale factor 3 parallel to the x-axis. So the same transformation can be stated in 2 ways. Parallel to the x-axis. Okay, so now let's see how to achieve this transformation. So to achieve this transformation, what we have to do is we have to find the transformation matrix. And we'll see later as to how to find the individual transformation matrices, but as of now, I'll just state the matrix directly. So this is the horizontal stretch by scale factor 3 about the x-axis matrix. Okay, so the next step to achieve this transformation, what I'll do is I'll multiply 1, 2 with my matrix 3, 0, 0, 1 from the left side. So if I do this on simple matrix multiplication, I'll realize I'll get 3 and 2. That means what has happened is my y coordinate remains the same, or the y component remains the same, and the x value and the x coordinate gets scaled by a scale factor 3. So it becomes 3, 2 here. So this is my new vector. I'll just color it with a different color. So this red vector here, which points from the origin to 3, 2, is my new vector, which is obtained by horizontally stretching 1, 2 by scale factor 3. Okay. Now my question is there any vector in this plane so that if you apply this transformation on it, 3, 0, 0, 1, it doesn't change direction? So that's my question. Is there any vector in this plane such that if you apply this transformation of horizontal stretch by scale factor 3 about the x-axis, it points in the same direction or basically doesn't change direction? Just pause the video and take a moment to think about it. Difficult to guess. All the vectors which are perpendicular or pointing in the upward direction or are parallel to the y-axis are the ones which will remain unaffected by this transformation. So for an example, if I consider a vector from the origin to 0, 5, or I'll just write the vector notation directly. If I consider the vector 0, 5, Let's see what happens if I apply this transformation on the vector 0, 5. So accordingly, what I'll do is I'll multiply 3, 0, 0, 1 with the vector 0, 5. So if I do this, the resultant vector will be 3 into 0 plus 0 into 5, which is 0. And down I'll get 0 into 0 plus 1 into 5, which is 5. So what we've seen is if I multiply any vertical vector parallel to the y-axis, if I multiply the transformation matrix with it, for example 3, 0, 0, 1, if I multiply with 0, 5, the resultant vector is same in magnitude and in direction as well. So with this, I'll write down an informal definition of what eigenvectors are. So eigenvectors are those vectors such that on the application of the transformation matrix, they remain parallel or become anti-parallel. So that means if I apply the transformation matrix on eigenvectors, either the vector will remain in the same direction or it'll point in the opposite direction. In any other case, it won't be constituted as an eigenvector. Okay. So this is basically the definition of eigenvector. Now what an eigenvalue is the scale factor. So in this case 3, 0, 1, 0, 5. If I do the multiplication, I get the same vector, but the thing is the scale factor here is 1 because the vector hasn't changed magnitude. So this scale factor is called the eigenvalue. So the general form is if I have any matrix A with the eigenvector as x and eigenvalue as lambda. This is the Greek letter lambda. So the general form is if I multiply a matrix with its eigenvector, I'll get the scale factor, which is eigenvalue times the same vector or the eigenvector. So this is the general form or the expression for eigenvectors. Ax equals lambda x. And this is how you'll find them in textbooks. But the thing is, in the case of the transformation matrix 0, 3, 0, 0, 1, not the vertical vectors, but also the horizontal vectors are eigenvectors. Because what happens if I multiply any horizontal vector with the transformation matrix? So for example, if I consider the vector 4, 0, which is a vector parallel to the x-axis. Okay, so now if I multiply the transformation matrix 3, 0, 0, 1 with the horizontal vector 4, 0, what I get is 12, 0 on matrix multiplication. Now if I look at it carefully, what happens is 3, 0, 0, 1 multiplied with 4, 0 doesn't give me 1 times 4, 0. Or the vector doesn't remain of the same magnitude, but it becomes thrice of what its magnitude is. It becomes 3 times of 4, 0. So in this case, 4, 0 is an eigenvector of the matrix 3, 0, 0, 1, but the eigenvalue or the scale factor is 3. The eigenvalue is 3, which is this number here. So for 3, 0, 0, 1, or basically the matrix for horizontal stretch by scale factor 3, there are 2 sets of eigenvectors. One set of the eigenvector is the vertical eigenvectors, or basically as the example we took 0, 5 and one was 4, 0. But the thing is not just 0, 5. Any vector parallel to the y-axis, or basically any vertical vector is an eigenvector of the transformation matrix 3, 0, 0, 1. So if I consider any vector, be it 0, 5 or 0, 3 or 0, 1, or even pointing downwards 0, minus 1, 0, minus 2, all are basically eigenvectors of the transformation matrix with the eigenvalue 1. Okay, so as a case which constitutes everything, I can just say any multiple of the unit vector 0, 1 is basically an eigenvector of this matrix with eigenvalue 1. And similarly, any multiple of the horizontal unit vector 1, 0 is an eigenvector of this transformation matrix with eigenvalue of 3. Now let's jump into the formal procedure of finding eigenvalues and eigenvectors, because not always we'll be aware as to what transformation does the matrix represent. For example, if I have a general matrix which is 0, 3, 1, minus 2, for this matrix, literally, just by looking at it, it's impossible to figure out what transformation is this matrix representing. So in such cases, to still find the eigenvalues and eigenvectors, there has to be a formal procedure for every kind of a matrix to find its eigenvalues and eigenvectors. So now we'll go to the procedure. So as earlier stated, the definition of an eigenvector is that if I have a matrix A and I multiply it with its eigenvector, I'll get lambda times its eigenvector. So now to find the value of x here, what I'll do is I'll do a rearrangement. I'll take lambda x to the other side. So I'll get ax minus lambda x equals to 0. And then to make x the subject, I'll isolate x or take x common from both the terms here. So I get a minus lambda I is equal to 0. So a lot of students ask me, why is this I present here? This I is present here because this is the identity matrix. And if suppose the I is not present here, so I have a minus lambda here, which literally doesn't make sense, because this means that I'm subtracting a matrix with a constant. So this literally doesn't make sense. Matrix subtraction is not possible with a scalar or basically with a number. So I'll just write it as a minus lambda x is equal to 0. So to make x the subject here, what I'll do is I'll have to get rid of this a minus lambda I matrix on the left hand side. So to achieve that, I'll multiply it with its inverse on the left hand side on both sides. So a minus lambda I inverse into a minus lambda I x is equal to a minus lambda I inverse into 0. On the left hand side, I have a minus lambda I inverse, basically a matrix multiplied with its inverse, which will give me the identity matrix x I. So I into x is equal to 0. Now I into x basically means x only, so x is equal to 0. So this means if the inverse a minus lambda I exists, the value of the eigenvector is 0. Or basically in matrix form, I'll say with the two components, I'll say 0, 0. So I'll just summarize this here. I'll say if a minus lambda I inverse exists, the eigenvector is the null vector. The eigenvector is basically 0, 0. So for the existence of a non-zero value of the eigenvector, the procedure which we did to isolate x or to make x the subject shouldn't work. So the procedure wouldn't work if a minus lambda I inverse doesn't exist. So if a minus lambda I inverse doesn't exist, we get a non-zero value for the eigenvector. And a minus lambda inverse won't exist only if the determinant is 0 or a minus lambda I is singular. The matrix a minus lambda I is singular. So for the existence of a non-zero value for the eigenvector, the determinant of a minus lambda I should be 0. So this is basically a condition which we'll use to find the eigenvalues. And once we know the eigenvalues, we'll move on further to find the eigenvectors. So as an example, I'll consider the same horizontal stretch scale factor 3 matrix, which is 3001. So example, so for 3001, I'll firstly create the A minus lambda I matrix. So my A matrix is basically my transformation matrix, which is 3001 minus lambda times the 2 cross through identity, which is 1001. Okay, now the next procedure is multiplication of a number with a matrix. So if I do that, I'll just have to multiply this value with each and every term here. So I'll get lambda 0, 0, lambda. And then I'll get 3 minus lambda 0, 0. and 1 minus lambda. So this is my A minus lambda I matrix. Now the condition to find the eigenvectors is that I'll equate the determinant of this equal to 0. So I'll say determinant of this entire matrix, which is 3 minus lambda 0 0 1 minus lambda should be equal to 0. And using the determinant formula, this simplifies to 3 minus lambda into 1 minus lambda minus 0 is equal to 0, which gives me, on simple solving, it gives me lambda is equal to 1 and lambda is equal to 3. So these are the two eigenvalues which I've got here using the formula, which is exactly equal to the eigenvalues which I got by understanding the transformations as well. Now I'll move on to the next step of finding the eigenvectors. So to find the eigenvectors, I have to do the procedure for both the eigenvalues separately. So I'll move back to the normal definition. So the definition was ax equals to lambda x, and I took lambda x to the other side. I got ax minus lambda x equal to 0. Then I took x common. I'll get a minus lambda I x is equal to 0. Okay, so I'll make use of this condition to find the eigenvectors. Okay, so firstly, I'll do the procedure for lambda equals 1. So for lambda equals to 1, to compute the A minus lambda I matrix, I'll substitute 1 in this matrix here, which is 3 minus lambda 0 0 1 minus lambda. So I'll get 2 0 0 0. And the eigenvector I'll assume with unknown components A and B is equal to 0 0. So my objective here is to find the value of A and B. So to do that, I'll do matrix multiplication. So 2 into A plus 0 into B is equal to 0. And then 0 into A plus 0 into B is equal to 0. So technically the second equation doesn't matter because it says 0 equal to 0. So I'll just disregard it. The first equation is 2A plus 0B is equal to 0. After solving, I'll get 2A equals 0, which means A is equal to 0. So though I had two equations, but the thing is, it just gave me one value, which is the value of A equals to 0. So that means the value of B can literally be anything because there are no bounds on it. So I'll say any vector of the form 0B is basically an eigenvector of this transformation matrix. Okay, so which can be written as any multiple of 0 and 1. So any multiple of, or basically 0 1 times B, or any multiple of 0 1 is an eigenvector with eigenvalue 1. For the eigenvalue lambda equals 3, we'll do the same procedure. We'll find the matrix A minus lambda I. So in this case, I'll substitute lambda with 3. So the matrix will become 0 0 0 and 1 minus 3 is minus 2. Minus 2 times, again, unknown components A and B, which will give me 0 0. Okay, now if I do matrix multiplication for the first equation, I'll get 0A plus 0B equals to 0 and 0A minus 2 times B equals to 0. So the first equation is nothing but 0 is equal to 0, which is of no use at all. The second equation implies minus 2B is equal to 0, which means B is equal to 0. So in this case, I'm getting the quite opposite condition. I'm getting that B is equal to 0 and A can literally be anything. That means all the multiples of the vector 1 0. That means all the horizontal vectors. So A for 1 0 is an eigenvector with eigenvalue of 3. Next, we'll consider a different transformation, which is 90 degrees anti-clockwise rotation about the origin. Anti-clockwise rotation about the origin. So for example, if I have a vector 1 2 in 2 dimensions and I want to rotate it 90 degrees anti-clockwise. So to get the new coordinates, what I'll have to do is I have to multiply 1 2 with a 90 degree anti-clockwise rotation matrix, which is 0 minus 1 1 0. We'll see later as to how this transformation matrix is derived. So if I multiply here, I'll get minus 2 and 1. So that means if I rotate 1 2 90 degrees anti-clockwise, I'll result in a new vector which is minus 2 1. Okay, so now the same question. Is there any vector in this plane such that if you apply 90 degrees rotation on it, anti-clockwise rotation on it, it points in the same direction? is there any vector in this whole 2D plane? So the answer is pretty straightforward. There is literally no vector. There's no vector in this 2D plane such that if you apply 90-degree anti-clockwise rotation on it, it points in the same direction. So let's see algebraically what happens if I try finding the eigenvalues and eigenvectors in this case. So my matrix A is 0, minus 1, 1, 0. So next I'll find the matrix A minus lambda I, so which I'll write directly now, which is minus lambda, minus 1, 1, minus lambda. Next, I'll equate the determinant of A minus lambda equals to 0, which gives me lambda square minus 1 equals to 0. I'll get lambda square plus 1 is equal to 0. So it results in lambda square being minus 1, for which there are no real solutions. So there are no real eigenvalues. In fact, non-real eigenvalues itself have a lot of significance, which is an interesting case. In fact, it's a good case study, but it's beyond the scope of AIHL syllabus. So if time permits, later after the course ends, we'll see as to what imaginary eigenvalues do. Okay, then we'll end on this note. We'll continue in the next lesson.